modeling mechanical waves. Does that happen to you? Lightning, you wait, then you hear the thunder. Why is this? It's because the speed of light and the speed of sound travel at different rates. Light is much faster than sound. What do you think what factors do you think affect the speed of a sound wave? Sound, all sound begins with vibrating matter. And then those vibrations move as longitudinal waves through matter in all directions. Now, depending on what type of matter, that will affect how fast the speed of sound is. The closer together the particles are, the faster the compression wave travels. The faster the faster the compressions will travel. Here it is right there. The faster the compressions will travel through that matter, which means that solids are the fastest, followed by liquids and then gases. Now, air is a gas, and since we live in air, the speed of sound is a lot slower than it would be if we were dolphins. There's another factor that affects the speed of sound, and that's the temperature of the air, or whatever the medium is. Let's talk about air. In my house right now, it is 20 degrees Celsius. That is what is called room temperature. The speed of sound at room temperature is 343 meters per second. However, that will change based on the temperature. The warmer it is, the faster sound goes. And we can use this formula, 331 meters per second. And then we can add, oh, by the way, that's the speed of sound at 0 degrees Celsius, which is the point where water freezes. All right, so right there that's 32 Fahrenheit. That's what we use, 0 degrees Celsius. At that temperature right there, sound travels at 331 meters per second. And then for every degree after that, the speed of sound increases by 0.6 meters per second. So if I wanted to figure out what the speed of sound was at 20 degrees Celsius, what I would do is I would take T being 20 degrees Celsius, and I would multiply 0.6 meters per second to that. All right, so it'd be 20 degrees times 0.6 meters per second, and that is equal to 12 meters per second. So I'm going to add 12 meters per second to the 331 that I started with. Okay, so I add those two numbers together and I end up with 343 meters per second, which is really good news because it matches up with my prior slide. So what would it be at 32 degrees Celsius? Well, that would be 32 times 0.6, which is equal to, figure that out yourself. All right, then you would add that number to 331 and you would get your answer for 32 degrees Celsius. Let's apply this information. Let's apply this information. Let's say it's 20 degrees Celsius and you see a bolt of lightning, and exactly 4 seconds later you hear thunder. How far away is the lightning? In order to do this, we need to use our old friend speed, distance, time calculation. And let's remember, we go back in our notebook and remember that speed is equal to distance divided by time. So I put the speed is distance over time. And it's asking me how far away is the lightning. So distance is equal to speed times time. All right, so I set up my T table as like that. Speed is equal to, time is equal to. Now let's remember, we just figured out the speed of sound at 20 degrees Celsius. We just figured this out. That's 343 meters per second. We just got that on our prior question. And 4 seconds is the time. Okay, so now we're going to multiply the two numbers together based on the formula triangle over here. We're supposed to multiply. So we've got 343 meters per second times 4 seconds. Looks like to me I can go boom, boom, circle, right? I got a numerator and a denominator, second. And I can circle my remaining unit, the meter. So let's see, boom, boom, circle. And I just circled the meter and I bring that over. It's good news because it asked me about how long or how far. So then I multiply 343 times 4, and the answer is in meters. You might want to even take that into kilometers by dividing by 1,000. Make it a little bit more appropriate. Another thing we could talk about sound is using sound waves. And one of the ways that sound waves are used is what is called ultrasound. So how are sound waves used? Well, one of the ways that sound waves are used is as a, by nature, echolocation. Some organisms have figured this thing out through natural selection. We use it in the medical community, what is called ultrasonography, and military use, and now it's civilians use it too, which is called sonar. All right, so let's talk about that. But in each case, it's this ultrasound, which is oftentimes used for this purpose, which are frequencies higher than 20,000 hertz. Two organisms, two animals, but there's a lot of other animals besides that, including whales, that use reflected sound waves to identify locations of objects they cannot see, is called echolocation. So this is one practical use of that as an adaptation, right, that organisms have to help them compete and survive, echolocation. And they oftentimes bats and dolphins use echolocation to find fish and prey. Right, so they use it for hunting purposes. They can actually hunt in the dark. They use reflected or this echoed sound wave, this reflection that comes back to the organism to determine how far away it is. Please watch the videos that I have on the Tuesday lesson. You'll learn more about it. During World War II, humans figured out sonar, all right, which is to find enemy submarines. We learned actually about this in 7th grade. We were covering seafloor spreading, and we learned about the Mid-Atlantic Ridge, because that's another practical application is that they use sonar to determine originally the distance to seabeds, mapping out seafloors. We now use it for fish finders. All right, that's what I use it for, to help me find the fish. You probably ever watch Wicked Tuna. All right, beep 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 beep. Okay, and then okay, you ever watch that? Good stuff. If you haven't seen that, sound navigation and ranging. That's what it stands for. Sonar. SONAR. I guess sound. I guess sounds better. Otherwise, you needed a vowel. So you got that sonar. Now you've also got the medical community. Watch this video, you learn a lot more about it. However, the first time we ever see our children, it's oftentimes through an ultrasound. Okay, and that's where you can see through the body. It's non-harmful. That's the best part about it, right? Best part. Otherwise, we're not going to use X-rays to find out where we're going to damage the cell. Okay, so one way they can see through the body, and in fact, we find out to determine if the unborn child, we can find out the gender sometimes, ahead of time. That way we can plan a little ahead. All right. Some of us like to wait. As opposed to sound waves, let's talk about another type of mechanical wave, another wave that travels through a medium. Now, in this case, the medium is Earth. And now those are earthquake waves known as seismic waves. This is the energy that gets transmitted as a result of an earthquake, a dramatic movement of Earth's plates, the tectonic plates. Speaking of tectonic plates and seafloor spreading, when Earth moves, we get earthquakes in a certain spot, and that energy transmits through Earth's surface. And there's 3 different ways that it transmits: P waves, primary, secondary waves, and surface waves. Primary waves are shown in red, surface waves in blue, and S waves in blue, and then the surface waves over here on top, little squigglies on top. Notice that the P waves will travel through liquid Earth's core. Travel right through it. No problem. Solids, liquids, gases, got that. You can do it. S waves, on the other hand, will not travel through Earth's liquid outer core. They get bent. Okay, they get pushed out of the way, making what is called a shadow zone. Because of this, we know what Earth's core or composition looks like. All right, because of earthquake waves, because of seismic waves. Listen, hopefully you guys can figure a little bit more about this out. By doing your PLIX, some of the PLIX was about this very thing. All right, so scientists study seismic waves to learn about earthquake epicenters, which is what your lab is about, and Earth's interior. All right, so let's see, seismic waves. Okay, so there's two different types of seismic waves. Typically, we already talked about there's three different waves, but two of them are called body waves. And they're body waves because they travel through the Earth itself, through the Earth's interior. Surface waves, on the other hand, travel on Earth's surface, right, as it would imply. Now, it turns out the surface waves, since we live on the surface, these are the ones that cause most of the damage during an earthquake. However, body waves, which travel faster than surface waves, body waves are how we determine epicenters of earthquakes, like time differentials. All right, so we have over here, we got this is the P wave would be the primary wave, then you get your S wave, and this is like a reading from a seismograph station, and this is how you determine how far away earthquakes occur from certain areas, and that's how we determine where an earthquake actually occurred, and that's how we know where plate boundaries are, and that's how we know that we live right next to the San Andreas Fault. All right, so let's talk about body waves. First of all, body waves are the S waves and the P waves. These are the two types of body waves, and they travel at different speeds. And these are what are used to determine the composition of the Earth. All right, so remember that S waves will not travel through Earth's outer core. However, the P waves will travel through Earth's core. All right. So solids, liquids, gases, P wave, no problem. S waves, and I have a problem. I can't do that because we're compression waves. We can't travel through that matter like that. Okay. S waves being the transverse waves will go right through it. All right. So one of the things that's big difference between these types of waves, besides the fact that they travel at different speeds, is one's a compression wave, a longitudinal wave, and the other one is the P wave is a transverse wave. All right. So the P wave, the transverse wave, is fastest. As you can probably imagine, it's easier to go through, travel at 7 meters per second, and therefore they're the first waves to reach the seismograph station, seismometer. And remember, a P wave can travel through anything, no problem. Travel through solid, liquid, gas. I'm a transverse wave. Secondary waves, on the other hand, squishing rock. Okay, the S wave, the secondary wave travels about half the speed, and therefore they're the second wave to hit the seismic graph station seismometer, and the S waves only move through solids. All right, these are the compression waves. Okay, so the longitudinal. I always mix up those two names. They actually mean the same thing. Now, just through here. Surface waves, on the other hand, travel along the ground outward from the epicenter at about 2.5 meters per second. And these are the ones that are doing most of the damage in an earthquake. All right. So if you got the love waves, you can be moving like this, right? Like side by side, right? You got the love waves, okay, you can be doing this, going up and down. So, all right, sorry, those are the Rayleigh waves. Okay, those are the Rayleigh waves. Well, you got your love waves and you got your Rayleigh waves. All right. So you're gonna hopefully not feeling the love on the love wave because they move side to side. All right, so the last thing I want to say is the seismogram, which is this, indicates how far away an earthquake is from the epicenter. And this makes a circle around wherever station recorded this information. Then, then what you do is you try to determine where that tells you how far away the earthquake occurred from one point. All right, so in this case over here, so let's say in LA, you saw that it was like, 500 kilometers away from LA. So that means it's somewhere around here. We don't know exactly where it's at. But then you get one reading in Portland, you get another reading in Salt Lake City, and then you draw three circles, and whatever that intersecting point is, that's where the epicenter is, the earthquake. And sadly, that's right where we live. All right. So great example I found. Hope this makes sense. Hope this helped. See y'all on